Okay, hi again, ladies and gentlemen, and have a good time. Thanks for your coming. I'm pleased to introduce the next speaker, who is Professor Juan Carlos Valenzuela Tripodoro from University of Cadiz, Spain. And the title of his presentation today is Result on Neuroman Domination Type Problem in Graphs. Uh, Juan, please.
Thank you very much. Well, first of all, I would like to thank the organizer to give me the opportunity to participate in this interesting workshop, and of course, thank you to all of you for attending this session. My name is Juan Carlos Valenzuela Tripodoro, and the work I would like to tell you today is related with some new variation of Roman domination problem. In the classical graphs, and also we introduced this concept in FATSI graphs. I have divided this presentation in two main parts. The first devoted to the K-Roman domination, and the last part regarding to introduce this concept in FATSI graphs. I would like to say that the results contained in this presentation are collected in two papers. The first of papers is already published in the Bulletin of Iranian Mathematical Society, recently published. And the other is Roman domination in fuzzy graph, which is submitted and still is not published. Well, let me start by quickly recalling some basic concepts in domination. Also, I know that all of you are familiar with these concepts. A dominating set is a set of vertices with the property that every vertex not in the set has at least a neighbor in this set. Of course, you know the minimum number of these the cardinality of this dominating set is the domination number of the graph. In this case, we may dominate every vertex in the graph with only two vertices. And this classical parameter have another interesting variation, which is the total dominating set, which is still commented before, in which we require that not only the vertices outside the set should be dominated, but also the vertices in the set D have to be. That is to say that is the same that require that the induces a graph by the vertices of the total dominating set have not isolated vertices. There are a lot of papers devoted to study these classical parameters, both domination and total domination. And the question is that in some situations, you don't need to dominate the whole set of vertices of the graph. I mean, I don't know, in some situations, it is possible that a vertex of the graph, like this green vertex, was in some sense self-protected, and well, we don't need to have another vertex to dominate it. In this case, also the domination number for this graph will be 3. We only have to consider 2 vertices to dominate the remaining vertices of the graph. In some sense, this well, there is some problem with this image. Well, it's a well-known image. In some sense, this is related with the concept of Roman domination. This concept was, as you probably know, introduced in 2004 for Cocaine, Dreyer, and Hedeniemi. And basically, we we consider a set of vertices and assign labels 0, 1, and 2 such that any undefended place may be defended by a stronger place with a label 2. The formal definition is for a Roman dominating function is, as we said before, a function that assigns labels of the set 0, 1, and 2 to the vertices of the graph, such that any vertex with a label 0 must be adjacent to another vertices with a label equal to 2. This is to say the same that the set of vertices with a positive label is a dominating set in the graph. The set of vertices having labels 1 or 2 must dominate the graph. Of course, the minimum weight of such a function is known as the Roman domination number for the graph, and is also a very well studied parameter. As a consequence of this definition, we can note that first of all, there is a one-on-one relation between the set of all Roman dominating functions and the disjoint collection of subsets of the vertices B. I don't want to talk about partitions because, as you know, some of these sets may be empty. So I prefer to talk about collection of subsets. And also we can note that the set of vertices with a positive label is a dominating set because every vertex in the set V0, the set of vertices with f equal to 0, is always dominated by at least a vertex in V2. Another consequence is not difficult to see that we don't need to have any edge connected a vertex with label 1 with a vertex with a label 2 if the Roman dominating function have minimum weight. This is due because in this case we can change the label of the vertices of the vertex of V1 to a label 0, and it remains still dominates by the vertex, by the neighbor in the set V2. Also, we can see that any vertex in the set V2 must have at least one private neighbor in the set of vertices with a label 0, because it's not, we can change this label 2 into a label 1, and we still have a Roman dominating function, but having less weight than the previous one. Well, all these basic properties are used to obtain many results regarding this parameter, and all. We can consider also the total Roman dominating function as a variation of the original problem, in which we require to a Roman dominating function to be a total Roman dominating function that the set of vertices with a positive label must to be a total dominating set. As I said before, this is the same that to require that any vertex with a positive label must have at least a neighbor in the set B1 union B2. Of course, the notation is the classical one. Gamma TR is the minimum weight of such a total Roman dominating function, and is known as the total Roman dominating number. Well, of course, there are a lot of results relating all of these parameters. It is well known that the the domination is less than or equal to total domination, of course, because every total dominating set is a dominating set. And maybe the first or the best known inequality regarding domain domination and domination is the one presented here, in which we can upper bound and lower bound the Roma domination in terms of the domination of the graphs. The first inequality is obvious because the set of vertices with a positive label is a dominating set, and so we may derive this this first inequality. And the second one, to prove the second one, we only have to consider a minimum dominating set and assign it to it the label 2 to prove that this inequality holds. We can also relate the Roman domination and total Roman domination in similar terms. And as I said before, I don't intend to show you a lot of results regarding these classical parameters because you are very familiar with all of these concepts. Well, I would like to say that in the last years, hundreds of papers have been published regarding many variations of this concept of Roman domination. We can enumerate some of them as the weak Roman domination, signet, restrained, independent, and so on. And maybe the one that I would like to tell you today about is related to the double, triple, or quadruple Roman domination, which we have generalized to the K Roman domination problem. In this case, a double Roman dominating function will be a function that assigns labels in the set 0, 1, 2, and 3 with the idea of generalize the Roman dominating function in the sense that, as I said before, the concept of Roman dominating function consists in that you have undefended place that must be defended by stronger neighbors in which you have a label 2. In this case, well, that really is the same that to think that you can send from a stronger vertex, you can send one unit to defend an undefended place. In the case of double Roman dominating function, the idea is that any undefended place could be defended not by one unit, but could be defended by 2 units. So that from the active neighbors of this vertex, you can send 2 units in some way to defend the undefended place. Here you have 2 examples of double Roman dominating function. Is in the graph of the left side, you only have a vertex with a label 3, although the remaining vertices are with label 0, but it is possible to send 2 units from the central vertex to any other vertex in the graph, so you can defend it. You can defend any undefended place. In the graph of the right-hand side, you have 2 strong vertices with a label 2, and the remaining vertices can be defended because any of them is adjacent to both the stronger places, so that they can be defended by 1 unit from each of these vertices. Well, in the analogously at the previous case, the minimum weight of such a function is known as the double Roman domination number, and we follow the standard notation as in the previous cases. Well, some years ago, Anger et al. Generalized this concept to K Roman dominating functions, in which the idea is that you can send from any close neighboring of a vertex of a undefended vertex, you can send K units to defend any undefended place. Formally, we can translate this situation requiring that the function that labels the vertices with label 0, 1 up to k plus 1 must to verify this condition here. No, the value of the sum of the levels of the closed neighborhood of a vertex must be at least k plus the cardinality of the active neighbors of the vertex. Here you have an example of this definition in which vertex U has label k minus 3. So we need to be able to send 3 units from its closed neighborhood. In this case, we can send 2 units from the vertex labeled with a 3 and 1 more from the vertex labeled with a 1, so that the condition is verified. The idea has, as I said before, is that any undefended place is defended by correlation from active neighbors. Well, one can think that this problem is a trivial translation of Roman domination, because, of course, if you consider a Roman dominating function in a graph, and you change label 1 to label k and the labels 2 to label k plus 1, of course, you obtain a function that satisfies the definition of a k-Roman domination function. But the fact is that is not an optimal strategy to obtain the minimum, because, for example, in this case, also this automatic translation is a k-Roman dominating function, but it's not an optimum. It's not a function with a minimum weight, because we can consider, for example, k to be in this case even, and we can assign this label to these vertices, obtaining a function with minimum weight. So what I want to say is that the path from Roman domination to k-Roman domination is not a trivial one. So it is worth to study this problem, because we can obtain some interesting results. In fact, we have proved that, well, we have found some bounds, because it's not easy to find the exact value for this parameter in graphs, even if we consider particular classes of graphs. And so we consider that it's very interesting to prove upper and lower bounds, and to prove that they are tight or fine. No? In this case, we have proved a first inequality in general for any graph that is almost, we can say, trivial, because in this case, you only have to assign this label to any vertex in the graph, and you obtain the inequality. And we prove that the equality holds if and only if the graph is the graph K2. To prove this fact, we can consider, well, it is clear that if the graph is the graph K2, it is clear that the equality holds. In this case, the parameter is k plus 1 that is equal to the value of the bound. But in general, if we assume that the equality holds, without loss of generality, we can assume that k is odd. If we have a strong support vertex, we can define a new function in this way, to giving the label k plus 1 to the strong support vertex, and the label 0 to any of its leaves. If the support vertex is a weak one, then we can define the function on this way, by assigning the label k to the leaf and 0 to the support. And in both cases, we obtain a function whose weight is less than the number of the k Roman domination number, which is a contradiction. So it must happen that the minimum degree of the graph is 2. But in this case, it's so easy to consider any vertex of the graph, assign it the label 0, and to the remaining vertices, assign it the label k plus 1 over 2. And by counting, you can achieve that this function will be a k Roman domination function with weight less than the minimum number, which is again a contradiction. So the only possible case is that the graph will be the complete graph with 2 vertices. Well, regarding the complexity of the decision problem associated to this Roman domination variation, in 2021, it is proved that the triple Roman domination is NP-complete for bipartite and chordal graphs. This is the k Roman domination problem for k equal to 3. A couple of years later, the general problem was also proved to be NP-complete for bipartite and chordal graphs. And recently, Pouredi and Fatali proved that the triple Roman domination problem is NP-complete even if we consider star-convex and convex bipartite graphs. In this sense, we have proved in this paper that the general problem of the k Roman domination decision problem is also NP-complete for this kind of bipartite graphs. Of course, the whole proof is a little bit larger, and we have to do some computation. But I would like to give you some sketch of the proof. We have proved it relating the k Roman domination decision problem with an instance of the 3-SAT problem that is a well-known NP-complete. And what we made is to consider a gadget for each element of xy of the set x of the instance of the 3-SAT problem. And then we construct a bipartite graph such that we are able to prove that the instance of the 3-SAT problem is satisfiable if and only if we are able to find a k Roman domination function in the associated bipartite graph with a given maximum weight. Well, this gadget that we construct for each element xy of the instance of the 3-SAT problem consists in 2 extra vertices, xy minus and xy plus, and 2 sets of k plus 1 vertices, y, and another set of k plus 1 vertices, z, such that the y vertices are adjacent to the vertex, to the central vertex, sy, and the other set of k plus 1 vertices are each of them adjacent to both the extra vertices xy plus and xy minus. By considering this gadget for each element xy, we construct the bipartite graph associated to the instance of the 3-SAT problem by adding another vertex t that will be adjacent to each and every extra vertices, x plus and x minus. And we also add one vertex for each of the clause of the instance, such that they are joined to the corresponding elements in the set of extra vertices. For example, in case of the clause C1, which is x1 minus, x2 plus, and x2, x3 plus, this vertex will be joined with the corresponding extra vertices in the graph. Of course, this is a bipartite graph, which can be constructed in polynomial time, so that the only thing that remains to make is to compute the weight of k Roman dominating function regarding the satisfiability of these clauses for the instance of the problem. It's not so difficult, but it implies some computations. Well, regarding once we have proved that the problem is NP-complete, the problem to find the exact value of the parameter in general is NP-complete. It is worth to have some bounds to be able to estimate the value of this parameter for some classes of graphs. So in this sense, we have proved several upper and lower ones, and of course, we tried to prove tight bounds and proving that these bounds are achieved for some graphs. No? In this case, we have proved that for a connected graph, we can upper bound the parameter for this expression. This result was also proved independently by other authors, Halali and all. But now in this paper, we add some information about the extremal graph achieving the bound. To prove this bound, we consider a vertex of maximum degree, vertex B, and we define a k-Roman dominating function as follows. No? We assign to this vertex with maximum degree the label k+1. To all of its neighbor, we assign the label 0. And for the remaining vertices in the graph, all of them will have the label k. It is easy to see that this is a k-Roman dominating function because the only vertices which are undefended are neighbors of k+1 label, so they are k-Roman dominated. And of course, the weight of this function is an upper bound for the minimum value of the parameter. No? Well, we can improve this bound, but to do that, we need to require some condition to the graph in terms of the minimum and maximum degree, or even for structural parameters like the girth. No? In case of this, of the next result, if we have a graph with minimum degree at least 2, and we know that the girth is at least 5, we can improve a little bit the previous bound by the expression we show in this result. In this case, we can reduce the label to assign to the vertex of maximum degree to k, and also, of course, we assign the 0 label to its neighbors, but we can also reduce the label that we assign to the remaining vertices as, broadly speaking, to half of the previous case. Why we can do it? Because, of course, the vertex B is self-protected, but the remaining vertices, because the minimum degree is 2, the remaining vertices must have another neighbor in the graph G minus B, and also as the girth is at least 5, every vertex in this graph must have a neighbor with a label, having a label k+1/2. So it is easy to see that this is a Roman domination, k-Roman domination function, and the weight is exactly the bound we were going to prove. In this case, this bound is easy to see that is achieved for the cycle graph C5. And another result that we have shown that improve the previous one bounds are regarding to connected regular graphs with, in this case, girth at least 7. We have proved that in this case, it is possible to have an upper bound that improves the previous one, and also this bound is fine for the cycle C7. And the next result if we require that the minimum degree is 3 and the guess is at least 7, improve the result obtained in the proposition 3, and also we can see that for 3 regular graphs, improve the result of proposition 4. Well, to finish with this section of bounds, I would like to talk about 2 more results. Not even for the tightness of the bound, but because we use some different techniques. In this case, in proposition 6, we use probabilistic reasoning to obtain this bound by considering a fixed set of vertices M, and consider the probability of probability P of a vertex, of any vertex B to belongs to this set. Well, it's not difficult to obtain the awaited value of the size of M and also the size of the complement of the closed neighborhood. And by using some calculus techniques, we can bound this expression in terms of the exponential function, and we can compute the minimum P that permit us to obtain this bound in terms of the order of the graph and the minimum degree. And finally, we have proved a lower bound. And in this case, we make use of a discharging procedure with the initial charge equal to the value of a minimum K Roman dominating function. And well, I guess that you know what this is a discharging procedure and how this works. We give an initial charge to every vertex in the graph, and then we apply some rules to discharge the initial charge of a vertex to its neighbor, so that the total is not changing. In this case, the only rule we have applied is that every vertex with a charge equal to J must send to its 0 neighbors some quantity. In this case is J minus 1 times K plus 1 over this quantity here. And after some computations, we can estimate the final charge of any vertex in the graph by considering some monotony properties of this function of J, and we are able to prove that the final charge for every vertex is at least this quantity, K plus 1 over delta plus 1, so that lead us to the result. Well, regarding exact values, as I said before, it's not easy to compute the exact value for the K-Roman domination function, even for particular graphs. No? In this paper, we have studied the smallest values of the parameter. In proposition 8, we have proved that the only graph that have this parameter equal to K is the singleton graph, and the graph that have the parameter equal to K plus 1 are those that have an universal vertex. Also, we have proved that it's impossible to find a graph having the K-Roman dominating number equal to K plus 2. And the last result we have proved is that, well, it is possible to compute the K-Roman dominating number for the path graph in terms of the congruence of the number of vertices modulo 3. Well, I think that this is all I wanted to say you about the K-Roman domination number, and I would like to finish this talk with some concepts and some results about the Roman domination in FATSI graphs. Well, in 1975, Sade introduced the FATSI set theory. In this case, we are familiar with graphs in which we have vertex and we have edges. And one edge is or is not in the graph. But in case of FATSI theory, we have a membership grade, which is a number between 0 and 1, assigned to each element of the graph. Well, many authors have been studied for a long time concepts regarding to classical parameters in graphs like connectivity or coloring or topological indices, but in the underground of in the background, sorry, of FATSI theory. Well, formally, a FATSI graph is a set of vertices and two membership functions, sigma and mu, that, as I said before, are numbered in the interval 0, 1. Sigma is the membership value of the vertices, and mu is the membership value of the edges, but satisfying the condition that mu is a FATSI relation with respect to sigma function, which means that the value of the membership for the edge is always less than or equal to the minimum value of the membership value for its n vertices, which in some sense we must understand that it's logical, because it has no sense that an edge exists in the graph if the n vertices does not. So if we think in the membership value of the edge as the probability that this edge is present in the graph, it's logical that this value must be less than or equal to the membership of the n vertices. With keeping this fact in mind, we can define some basic concepts similar to the ones on classical graphs. In this case, a FATSI path is a set of ordered set of vertices in which every internal edge has a membership value positive. We call the strength of a path, or the connectivity strength of a path, to the minimum of the membership values of its edges, of the internal edges. And these couple of concepts are very important in this work. We call effective edge to an edge that achieves the maximum possible value. That is to say, is an edge that have a membership value equal to the minimum of the membership values of its n vertices. And on the other hand, a strong edge is an edge that its membership value is greater than or equal that the connectivity strength of any other path joining these n vertices. In some sense, a strong edge is an edge that represents the better or the stronger path to go from U to V. This concept of a strong edge will play a central role in this paper. Well, we have to know that first of all, every edge in a path is a strong edge, because, as I said before, an edge is a strong edge if there is no other path joining the final vertices that are stronger, no? But in the case of a path, there is no such path, so every edge is a strong edge. And second, every effective edge is a strong edge. Well, recall that an effective edge is an edge that achieves the maximum possible value. So for what is an effective edge and a strong edge? Because if mu of UB is maximum, so the strength of this path is less than or equal to the value of the first edge U sit 1, and also is less than or equal the value of this last edge V sit 2. So the strength of the path must be less than or equal the minimum of these two values. But the minimum of these two values is exactly the value of mu of the edge, because the edge is effective. So we have that for any path P joining U and V, the membership value of the edge is less than or equal. So we are done. For example, in this case, we have a FATSI graph with 4 vertices and 4 edges. And for example, the edge on the left-hand side, this is a strong edge because the only path joining these two vertices is the path with connectivity, with a strong connectivity equal to 0.2, which is less than or equal to the edge. So this edge will be a strong one. The same happened for the underlying edges, but in the case of the edge that have the mu equal to 0.2, the strength of the path joining the two vertices is 0.3, which is greater than the strength of the edge. So this edge will not be a strong edge. If we add this new edge to the graph, of course, this edge is a strong edge because this is the maximum value in the graph of the function mu, but the graph on the edge on the left, which will be before a strong edge, now is not, because you can have this path joining the n vertices that have a strong a connectivity strength equal to 0.7, which is greater than the strength of the edge. Well, based in the concept of strong edge, we can define the similar concepts to that we know and we have in classical graphs as the degree. But in this case, we have different ways of defining the concept of degree. In this case, we can define the degree of a vertex as the sum of all the membership values of all the edges incident with the vertex, or we can speak about the strong degree, in which we only assume the value of the edges that are strong. Similarly, we can define the strong neighbors degree of a vertex, in which instead of sum the strength of the edges, we assume the membership value of the vertices, which are strong neighbors of the original one. And similarly, as usual, we can define the minimum and maximum degree, strong degree, and strong neighbors degree. Well, we also denote mu s of a vertex as the minimum value of the membership value of its strong edge for every strong neighbor of the vertex. We denote by mu min the minimum value for mu s in the graph, and analogously the maximum. And we consider the number p as the order, the sum of the membership value of the vertices at the order of the graph, and q will be the sum of all the membership value of the edges at the sides of the graph. And we have to distinguish between the cardinality of a graph, which is the usual concept of cardinality, the number of elements, and the scalar cardinality of a set in a FATSI graph, which is the sum of the membership values of the vertices belonging to the set. Well, finally, we define the complement of a fuzzy graph, having the same set of vertices, but by considering the complement of the membership value mu as the complement value of the function mu with respect to the maximum of the membership value of the n vertices. Well, let me show you an example to clarify a little bit this concept. For example, in this case, for the vertex B2, we have that the neighborhood of B2 is B1 and B3. So the degree of this vertex will be 0.2 plus 0.3 equals 0.5. But the strong neighborhood of the graphs is only B3 because the edge joining the vertex with B1 is not a strong edge. So the strong degree in this case is only 0.3, and the strong neighbor's degree would be 0.9, which is the membership value of the strong neighbor. Of course, the mu s of the vertex B1 match the value of the maximum of the value of mu in the graph, which is 0.9, and the corresponding to V3 is 0.3, which is the minimum also of the entire graphs. Well, some authors have studied some corresponding concepts in classical graph, but in the background of fuzzy graph. For example, our Ghanaian Chandrasekaran defined the strong domination set as a set that satisfies that every vertex outside the set is strongly dominated by a vertex in the set. This is similar to the concept we define in classical graphs. The strong domination number, of course, is the minimum scalar cardinality of a strong dominating set. We have to keep in mind that the scalar cardinality is not the number of vertices in the set, but the sum of the membership values of these vertices. And finally, the Sunitan author defined the strong domination number in terms of a strong edges. It's a little bit different. Instead of consider the sigma value, they consider the strong domination number as the minimum sum of the mu s of the vertices. Well, in classical graph, we define the Raman domination function as we have commented some minutes before, and the Raman domination number was the minimum weight of such a Raman dominating function. In this case, we introduced the concept of a strong neighbor Raman dominating function in a similar way by assigning labels to the vertices 0, 1, and 2, such that every 0 vertex has a strong neighbor with label 2. In this case, we use the concept of strong neighbor. And also, to compute the weight of a strong neighbor Raman dominating function, we use a concept similar to the one used by Sunita, computing all the products of the label of the vertices by the mu s of the corresponding one. Of course, the strong neighbor Raman dominating number is the minimum weight of such a strong neighbor Raman dominating function. Well, for example, in this case, we have the blue labels, which are the sigma values. The red one are the mu values, and the green one are the labels assigned by the Raman dominating function. In this case, we assign to this vertex the label 2, to this one the label 0, also this one, and the last half a label 1. Well, this in this case will not be a Raman dominating function, even if in the underlying graph if we forget the sigma values and the mu values, of course, we have a Roman dominating function in C4 because every vertex with a label 0 is adjacent to this one, which dominates it. In this case, not because this vertex does not have a strong neighbor which dominates. It's because this edge is not a strong edge, as we said before. No? Instead of, we can consider this other labeling of the graph in which we assign the label 2 to this one vertex, 0 to this other vertex here, and for this vertex we assign the label 1, and this is a strong neighbor Roman domination function because every 0 have a strong neighbor with a label 2, and also we have that the weight of this function will be this label times the minimum of the membership value of its strong neighborhood, so 2 times 0.5 plus this label 1 times the only neighbor, the only strong neighbor, for in this case, has 0.3 membership value, so the total weight will be 1.1. So in this case, this is a strong Roman dominating function in this fuzzy graph, but it is not difficult to see that it is not optimum, it's not minimum, because we can consider this other labeling of the graph that also satisfies the condition. And in this case, the total weight is 1, which is in fact is the minimum possible weight for a strong Roman domination function. Well, so in this work, we have introduced the new concept of a strong neighbor Roman domination number for a fuzzy graph, and we have studied some relationships with other parameters. We are trying to find some tight bounds to compute the exact value for several classes of graph, which is not, of course, easy in this case. And we try to characterize the extremal graphs for this, for the shown bounds. Well, let me show you an example because there is some particular things that happens when we try to study the Roman domination in fuzzy graph that are quite different to the situation that we have in classical graphs. For example, when we consider this Roman dominating function in this graph, we have that there are no edges, but the weight of this function is n. Instead, when I consider a fuzzy graph, in this case, the mu value is always 0. That is to say, we have not edges in the fuzzy graph. Even if the labels are not 0, we have the total weight for this graph, for this function is 0. So this is a very quite different situation relating to the study of Roman domination in classical graphs. Also, we can have some other problems. For example, when in a classical graph, we study the Roman domination in a cycle, it is well known that the optimum assignment of label is to give a label 2 here and 2 labels here. And so this is a minimum Roman dominating function in the cycle. In this case is C6. And for the Roman domination number is 4. But if we consider, for example, these fuzzy graphs, one can think that the strategy must be the same. But if we consider the same assignment of labels, we have, of course, a strong neighbor Roman dominating function, but the weight is 0.62. Instead of this, we can consider this other assignment of labels, this other strong neighbor Roman dominating function, in which we give a label 2 to this vertex and to this one, and also we give a label 1 to this other vertex. Of course, the 0 vertices are stronger dominated by its strong neighbors. And in this case, we have we achieve the minimum possible value for the strong neighbor Roman dominating number, which is 0.34. So what I would like to say in this case is that even using more labels, in this case, we use 2, 2, and 1, 5, we can have in FATSI graph, we can have a strong neighbor Roman dominating function with having less weight than if you use Roman dominating function with less label. And this is quite confusing because we are familiar with the strategy to find the minimum Roman dominating function in classical graph, and we always try to assign the minimum number of positive label in the graph. Well, regarding, I don't know if I have time.
Just 2 minutes, Juan.
Okay, 2 minutes. So I go quickly. I will give the details, but we have proved some results regarding these new parameters. The first is very similar to the well-known inequality regarding the Roman domination and the classical domination parameter. The proof is quite similar. I don't want to repeat it. We also characterize the graph attaining the upper bound, that is to say, the graph for which the strong neighbor Roman domination number is exactly twice the strong domination number. And we have proved that it is only possible for a graph without strong edges. Also, we have proved several results trying to bound this new parameter, the strong neighbor Roman dominating number in general. And for the last, we have tried to find the exact value for several particular families of graph. In this case, we have done it for the complete bipartite graph. As you can see, it's not easy to describe this number. In this case, it's not so easy as in the case of Roman domination. And also we have tried to do it in the case of cycles and FAXI cycles and FAXI path. Well, I think that this is all I would like to tell you today about. Thank you very much.
Okay, thank you very much, Juan, for your nice presentation. I learned about fuzzy graph and this Roman domination problem in fuzzy graph. Thank you so much. Is there any question or remarks? John, I think computation of the Roman domination number for fuzzy graph is not possible exactly, yes? Or just we must obtain an upper bound and lower bound based on mu, or I'm right or not?
Yes, you are right. We have tried to even to give the exact value by an explicit formula, even for the simplest graphs you can think as path or star graph or something like that. And it's very, very difficult. It's really difficult because it depends on the values of the membership function. So there are many, many different situations, and it's really difficult.
Yeah. Okay. Thank you so much. If there is no question, let's thank Juan again. Thank you, Juan, for nice presentation. Thank you so much.
Thank you so much for a very nice presentation.
Thank you very much for you, because I'm glad to be invited to this workshop, and I hope to see you again in the 4th workshop.